binomial expansions at the bottom of this screen and look for patterns. Now you can look for new patterns, or if you remember some patterns, these might jog your memory, some patterns that you maybe discussed in Honors Algebra 2. So the binomial theorem, which we'll talk about on the next slide, expands binomials. X plus y is a binomial. It has two terms. It's being raised to the nth power. So the binomial theorem does all the work, so you don't actually have to multiply x plus y times x plus y times x plus y n numbers of times. So this has the work all done. Here's x plus y to the 0, x plus y to the first, x plus y to the second. And what I want you to do is look for patterns over on this other side. Okay. So what kinds of patterns do you notice from term to term? Or from row to row? Those are the types of patterns we want to name because it's going to jog our memory of how we do binomial theorems. So kind of talk to your groups, and you guys might know some patterns from Algebra 2, or you can look at a row and try to find a pattern. Go for it. Try to find as many patterns as you can. There's more than one.
They added the exponent. The second row, there's a y. And you start with the first row, you get like coefficients.
Okay, let's come together and see what kinds of patterns we know. Dylan is ready to give us a pattern. Oh, what do you mean by powers of 11?
So like you have 11 to the 0, 1 to the second is 1, 2, 1, 2 to the 11 to the 11.
Oh, it really is? Oh, I didn't know that. Oh. Okay, good. Okay, so when you say they are powers of 11, you are referring to the coefficients. Okay, so he's saying, like this would be 11 to the 0. 11 to the first, 1, 1. 11 squared is 121. 11 cubed is 1,331. 11 to the fourth is 14,641.
Oh my god.
Does it not work anymore?
It still works. You just have to.
You have to like put the.
You have to like.
That was
bring
almost
the
super cool.
Oh, okay, that's cool. All right, awesome. I love that. I'm going to tell Mrs. Hillman to see if she knows. I'm going to tell all the math teachers and see if they know. Okay, other patterns. Thank you, Dylan. Emma.
There's the triangle thing where it's like, what is that called? It's like Pascal.
Oh, yes. Pascal's triangle.
1, 2.
Yeah, so if you don't remember Pascal's triangle, start with the triangle of ones. What I mean by that is like pretend there was a triangle there and there's a 1 in all the corners. And then every successive row will start and end with a 1 and have one additional term. To get the next term, add the 2 previous right above it. So we got 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, so those are also like a connection to our coefficients. Good. Any other patterns you notice besides the coefficients? David? Oh yeah, so that one was, someone was showing that to me before, and it's weird because it's not. It's it's like 1. This one. 1, 2, 3, 5, 8. That's weird. 4. Yeah. Okay, that is cool. I didn't know that one either, but third hour didn't tell me that. So cool. Okay. Other patterns in the expansions. Okay, yeah, so you probably talked with your group about the powers of the other two terms. So, like, let's look at the x plus y to the 4th. Look at the x's. Starts with 4, 3, 2, 1, and then this one must be x to the 0 because it's not there. When you look at the y's, it must be y to the 0, y to the 1st, y squared, y cubed, and then, of course, y to the 4th. Okay, so the first term is going down, and the second term is going up. Are there any other patterns you notice with the exponents? They always add to the value of n. I use that all the time just to, like, check my work. I have a really bad habit of, like, going down halfway and then starting to go back up again. Why? I don't know. I do it all the time. So I'm always checking my sum. Okay. Anything else that you want to talk about in terms of patterns from the left side to the right side that I'm missing? You guys do have some really cool patterns with Pascal's triangle, and hopefully you talked about that. We'll maybe talk about that again next week. But yeah. So here's what the actual binomial theorem looks like. So I'll give you a chance to jot this down. Here's the actual binomial theorem. It's essentially saying the patterns that you pointed out to me, but we'll talk more about that once you get written down.
This looks very nice.
So there is this like plus dot 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 in the middle, and it's just saying like it depends, right? At the top of the example that I had on the previous slide, there's only a few terms. Like if I square something, it has 3 terms. If I cube it, it has 4 terms. That's another pattern. There's always one more term in the expansion than the power of the binomial. So it really just depends on whatever your power is, how many terms you're actually going to have. But I am noticing the same patterns with exponents. So if I concentrate on the first term of the expansion, x, notice that it starts with the highest exponent, n, and then it goes down by 1, and then it would be n minus 2, and n minus 3, and n minus 4, until it gets down to 0, eventually n minus n, whatever that may be, however many terms there are. So that one's decreasing as you go from left to right. And then when you look at the second term, the y, it starts at the lowest, 0, and then it starts to go up. So it would be y to the 1st, y squared, y cubed, so on and so on, until you get to the very end and you're at y to the n. And we could also argue that the sum of the exponents is still n, right? N plus 0 is n, n minus 1 plus 1 is n, so on and so on. So we still have that sum. The one part that's like different in the binomial theorem is really this combinations part, right? Okay, so we had described really those coefficients as the numbers in Pascal's triangle. So that's really another cool part to Pascal's triangle. It's just made up of combinations. So that very first one is a combination of 0 items chosen 0 at a time. That's really boring. Pick nothing from nothing. There's one way to do it. And then in row 1, which is really like the second row, it's a combination of 1, choose 0, and a combination of 1, choose 1. If I have one item and I want to pick nothing, there's one way for me to do that. If I have one item and I want to pick one item, there's one way for me to do that, pick the item. Okay. And then that continues for the next row. So this is a combination of 2, choose 0, a combination of 2, choose 1, and a combination of 2, choose 2. I always do that on that last one. A combination of of 2 choose 1, combination of 2 choose 2. So what this is saying is if I have 2 items, there's always one way to pick nothing. And there's always one way to pick everything. Pick everything. That's why the front and the backs end with 1s. But in the middle there I have a combination of 2 choose 1. So imagine I have 2 students, Maddie and Brian, and I get to pick 1 student. How many ways can I pick one of 2 students? 2 ways, right? I could pick Brian, or I could pick Maddie. Okay? And so that's where this 2 comes from. And that just continues. Okay? So it's up to you. Sometimes the combinations are helpful. Like we'll do some examples where we don't want to do the full expansion. We just want to find a specific term. So then the combinations are probably best. When I'm usually actually expanding things, I'm probably using the rows of Pascal's triangle. So it's kind of up to you what you want to do. Okay? Let's do an example. We'll do 1 together, and then you'll try 1 on your own. Here's my example. We're going to expand x minus 3 to the 4th. Okay, now of course these are my notes. So I'm going to show all my work with the binomial theorem so I know how it works. Everybody okay? Oh, that's outside? Okay, what's the power of my binomial? 4. So all my combinations are going to be combinations of 4 choose. Okay. So I'm going to start in my expansion. I'm going to try to squeeze it in one line here. A combination of 4 choose, 0 to start, times the first term raised to the highest exponent would be 4, times the second term, which is negative 3, raised to the lowest exponent, which will be 0. And my 2 exponents, 4 and 0, add to make 4. And then I'm going to add a combination of 4 choose, 1. I'm going to increase my choose. My x is going to decrease in exponent, so it's going to go from 4 to 3. And my negative 3, the second term, is going to increase to 1. And I'll do another one, combination of 4 choose 2, x squared, negative 3 squared. All along I can be checking my 2 exponents. Do they add to 4? You may also be noticing another pattern here with the work. The number that you choose in the combination always matches which exponent? First term or second term? Second term. The combination of 4 choose 1, that matches the exponent for negative 3. Okay, combination 4 choose 0, that matches the exponent for negative 3. So the combination, the number that you pick, always matches the second term. That'll be helpful later on. Okay, and we can continue on with our work. Now, I would argue that probably a lot of you are not going to show all of this work if you're using Pascal's triangle, right? Some of you might skip out writing the combinations and you may just go straight to Pascal's triangle. Since it was being raised to the 4th, we want to go to that 4th row, if we consider a row 0, that starts out 1, 4. Okay. So can you guys tell me what are the other coefficients from that row? 6, 4, 1. Now, if you don't know Pascal's triangle and you don't want to recreate Pascal's triangle in 10 seconds on your paper, you can always use your calculator to do all the combinations. That seems like a lot of tedious work for just knowing a row of Pascal's triangle. Okay, now I'm going to finish out what the rest of this is. So now I'm going to apply my exponents. This is going to be 1 times x to the 4th times negative 3 to the 0, which is 1. The combination, the first term and the second term, these things are always getting multiplied, and then you're adding in between. Okay, so then I'm going to have another product of 3 items. The 4, the x cubed, and then a negative 3. 6, x squared, and 9. X times negative 27 times the 4 from Pascal's triangle, and then 1 times 1 times 81. I would guess more of you are probably like working off of those coefficients right at the beginning. That's how I teach it in algebra 2. And then the last thing you have to do is clean it all up, right? Do all the multiplications. So 1 times x to the 4th times 1 is just x to the 4th. This one is going to be 4 times x cubed times negative 3, so that's going to be minus 12x cubed. What do we get? Plus 54x squared minus 108x and plus 81. Okay. Seem familiar to us? Maybe? I love expanding a binomial. So relaxing. Just do a few patterns. Okay, now there's another good pattern here that we could note. If one of your terms in your binomial is positive and one of your terms is negative, what do you notice about the terms in the final answer? They're alternating signs, right? So that's another quick and easy check for you. If you see that one of your terms is negative, make sure in your final answer you're alternating your signs if the two are different signs. Okay. I get a lot of students sometimes who will do well on the first one, like they'll have positive, negative, positive, but then you just get tired of it, right? So you got positive, positive. But if you took a quick look at that, you would know the 4th term would have to be a negative. And since we're raising it to the 4th, we have an extra term, 5 terms. Okay. I want you to expand to x plus y raised to the 5th. Now, you don't have to worry about your alternating signs because you don't have a negative here. But there is one thing to kind of worry about. Does anybody know what people might miss? The coefficient, the 2x. Let's say in the middle of your work you're doing 2x, the first term raised to the 3rd power. What's that equal to? 2x to the 3rd. 8x cubed. So don't forget that you'll have to distribute your exponent to the coefficient as well as to the x. When you say the first term cubed, you mean 2x times 2x times 2x. Okay, go for it. See what you can get done before I go. So as I moved around the room, I saw people doing a really great job using parentheses for their 2x. I just want to do a couple of these so you can kind of see how this is going to work. If you want to just use your numbers from Pascal's triangle rather than calculating them in your calculator, this is the 5th row. So that's 1, 5, 10, 10, 5, 1. Okay, those are your coefficients from Pascal's. And then for the 2x terms, okay, remember 2x raised to the 5th means 2x times 2x times 2x times 2x times 2x. So not only does x get raised to the 5th, but so does 2. That would be 32x to the 5th. And then 2x to the 4th would be 16x to the 4th, 8x cubed, 4x squared, 2x, and 1. Okay, so don't forget about that. And then for the y terms, those are pretty easy. It's just y to different powers. So y to the y to the 0 is 1. And then we'll have times y to the 1st, y squared, y cubed, y to the 4th, and y to the 5th. Okay, so it's really that 2x raised to powers in the middle that you got to be careful with. If you simplify, so now you multiply, you'll get 32x to the 5th plus 80x to the 4th y plus 80x cubed y squared plus 40x squared y cubed plus 10xy to the 4th plus y to the 5th. Okay. Any questions? Like you're concerned your term may not equal my term, you don't know where my number came from? All right, so practice on these is really important. Usually the biggest errors that I see are people who don't know when to multiply parts and add parts. Okay, and to me that's like a practice issue. You've done the binomial theorem enough time that you know when you're multiplying, when you're adding. Oh, I did that in the second hour too. The 80, right? I don't know. 80x to the 4th y plus. And this one was 16. Okay. Is that better? Thank you. Anything else? Okay, now the last 3 examples are shorter. They're going to use the binomial theorem. And this is the case where knowing the binomial theorem has the combination out front is going to be super helpful, because we don't actually want to expand the whole thing. We just want to find a specific term. So we want to find the 5th term of a plus 2b raised to the 8th. Bless you. Okay, so here would be my suggestion, if you don't already know what's going to happen. Go back to the 2 previous examples we just did and count out to the 5th term. Okay, so I'm going to actually flip back to my other slide. You could use your finger on your own paper. I'm going to do it in my work. 1st term, 2nd term, 3rd term, 4th term, 5th term. Okay, so there was my 5th term in the first one. And then I'm going to scroll down a little bit. And of course we have different numbers, but I'm going to find my fifth term? First term, second term, third term, fourth term, fifth term. Even though we're changing the binomial, and we're changing like the power, so the numbers are different, what's always true when you're choosing the fifth term? Noah?
Y to the fourth.
The second one will be raised to the fourth, the second part of the binomial, and the combination will be choose 4. Why is it choose 4 instead of choose 5? Because you start at 0. So the first term is 0, the second term is 1, the third term is 2, so on and so on. If you want the nth term, you should do a combination choose. If you want the nth term, choose n minus 1. It's always the one before it. So for me to do these terms, I just think about the binomial theorem. There's 3 parts to every term. A combination, a first term, and a second term. And then I just try to fill in my total and my pick, and then my exponent. So of course it's going to be a combination of 8 choose 4. In this case, because my exponent is 8, they're of course both going to be 4s, but which one should always match the choose for the combination? The first term or the second term? Second term, Brian says. So this should be 4, and then of course they have to add to 8. So that would be 4. So I'm just using patterns to try to fill in the blanks there. A combination of 8 choose 4. Can anybody do that for us? 70. And then we're going to do times a to the 4th times 16, b to the 4th. So if I'm doing that, 2, 4, 1,120, a to the 4th, b to the 4th. So the coefficient is all the numbers, the combination and the 2 to the 4th multiplied together. Okay, you try this one. See if you can get the right 7th term for the binomial. You may need to get out a calculator. Find the 7th term of 3x minus 2y to the 10th. So again, I always start these off with like, there's 3 parts to every term. A combination, a first term raised to an exponent, a second term raised to an exponent. It's being raised to the 10th, so I'm going to do a combination of 10 choose. What'd you guys do? For the 7th term? 6. Okay, and that should match the exponent for 3x or negative 2y. Negative 2y. Therefore, 3x is being raised to the 4th. And then, I can't remember, it's like 1,088,640 would be x to the 4th, y to the 6th. So you have to do the combination of 10 choose 6 and multiply it by 3 to the 4th and negative 2 to the 6th. Like, should that term be positive or negative in the end? It should be positive because your negative is being raised to an even exponent. So if you type it incorrectly into your calculator, you can also use your numerical sense to make sure that you get the right sign. Okay, one final practice. Nope. Nope. Am I close? Good. Change up my question a little bit. Could you tell me what the coefficient to the a x to the 8th y to the 6th term will be in the expansion of x squared plus y to the 10th? So I'm basically asking you what's a, right? The coefficient. Well, every term is made up of three things, right? A combination, a first term raised to a power, and a second term raised to a power. I know that my binomial, power of a binomial is 10, so I'm going to be doing a combination of 10 choose something. And my exponents that I pick have to add up to 10. Do you know the exponent for either x squared or y? Y must be being raised to the 6th, because it's y to the 6th in the term, which matches the number that I'm picking. And therefore, x squared must be being raised to the 4th, which doesn't that give me x to the 8th? Some people get worried because 8 plus 6 is 14, and that doesn't match 10, right? But x squared is being raised to an exponent, so that changes things. So in this case, it's whatever 10 to the 6th is. We have no other numbers to worry about, so I think that comes out to 210, if I'm right. Okay. I'm going to put your homework up and give you 3 problems. You got about 5 minutes. You could get started on 1 or 2 of them. The first one is so easy, it'll be done in like 2 minutes. Okay, so see what you can get done.